Let's give a warm MongoDB local welcome to Henry Weller.
All right, can everybody hear me? Does everybody who have headphones on, we're good? Okay, great. Thank you everybody for coming. I'm Henry. I'm, as Ralph mentioned, one of the product managers for Atlas Vector Search. And today I'll be talking a little bit about data modeling. So sort of an old concept with MongoDB that's being made relevant again in the age of vector search and retrieval augmented generation. So before I talk about any of these concepts, I want to just take a quick second and reflect. So it's been about a year since we announced Atlas Vector Search in public preview. As Dave mentioned in the keynote, it is the fastest growing capability we've ever added to Atlas. We've got thousands of enterprises and customers using this product. And I really want to take a lot of the feedback that they've given us from that past year and help use it to improve the product. And maybe talk a little bit, before we even talk about improving it, about what people have tried, what has worked, what some of those learnings have been for folks that are still trying to build apps that they want to put in production. So a couple considerations. A lot of them might seem kind of obvious. Vector search is a methodology. So the fact that it can be used for multiple types of interfaces, not just RAG and more forward-looking interfaces, but things that we're very familiar with, like search experiences. This has been a huge driver of usage as well. We're also seeing a lot of people find a lot of value from vector search, but also hybridizing it with other techniques. We'll be talking about that towards the end of the presentation. And then kind of this bigger idea of what it means to build something, put it out, test with it, and then actually get it to production, and what some of those hurdles are. We're going to kind of start at a foundational level and try to see how we can iterate on the data model and the different tooling that we're using to make it more likely that you can bring your RAG app into production. So taking a little bit of a step back, I'm sure a lot of you have heard of retrieval augmented generation, so I won't go through the whole flow charts, but we're going to talk about each of the systems that you usually see. In this case, considering a retrieval augmented generation system built on MongoDB, the roles and responsibilities of each of them, how you can sort of build a mental model for where they might fit in, and how you can iterate and improve on each of them so that you don't have this sort of mass of things to consider in a totality. You're not thinking about how do I improve the relevance of the end product, but how do I improve each individual component. Naturally, we're going to start with MongoDB. This is a MongoDB conference. So taking a step back before we even talk about search, I think it's important to think about what is a database. Often when we hear about RAG, we think about it in the context of vector databases, but vector databases most often are search systems. A database is a little different from a search system. Databases are principally responsible for serving writes, or taking in writes from a user and serving reads, generally under high query load. You want to make sure that you can serve the most recent updates to your data, in this case a MongoDB collection, as new writes come in. You want to have ACID guarantees, and generally the way that you might improve reducing the computational load per query is by creating indexes on certain fields that you might expect to be filtered on. This way you don't have to do a full collection scan, and you are minimizing computational load, and that's really the primary objective of a database. You got to be available, you got to be consistent, you got to be distributed, you got to be scalable, but at query time, you're really dealing with a lot of filters, and in some cases, partitions and sort keys. There's kind of a whole other set of things you have to consider when building a search system. Sort of from the beginning, you need to be thinking about accuracy, relevance, right? You're not just dealing with filters, you're dealing with indicators of something being meaningful, which is very different from how traditionally a developer might think about a database. In the case of keyword search, which is probably the most broadly used type of search system, it's defining relevance by specific keywords that you've seen in your corpus that also might appear in a query. You might have another way of defining relevance, which could be coordinate-based. Maybe you're looking for an Arby's that is close to your home and has a specific kind of dish, in addition to that. So you're taking this problem of improving accuracy and adding on another system, ideally within the same system, but still you're adding another kind of computational load to the problem you're trying to solve, which is often merited, but can create sort of considerations. Dual optimization problems in general are more challenging. It's kind of an obvious statement, but it's worth remembering as you build types of search systems. Of course, like many other considerations might come in with the search system, similar to a database. As the amount of data scales up, the considerations you have to make and the kind of nature of the search problem starts to change. You might not be able to anticipate what right means. If you're defining question-answer pairs, you might not have an idea of what the right answer to an ambiguous query might be. And you might have very different query patterns depending on the use case of your system. You might have a chatbot or search interface that serves very different types of queries, like where should I go for dinner, or help me plan a trip to Japan. When we think about other methodologies that you can bring in to solve the search problem, that's when we think about things like vector search. Right? Keyword search has been a very mature sort of methodology that's been iterated on for decades. Vector search, powered by bidirectional encoders and transformer-based models like BERT, have produced vectors that are much more capable at representing relationships between tokens in a more generic way. But often that accuracy improvement comes at the cost of additional computational load. An inverted index for keyword search fundamentally does a lot less work than a HNSW or other vector type of index, which has to do vector comparisons, which are generally quite expensive. You could go even further. Maybe you want to get a broad set of results that's considered with vector search, and then re-rank them so that you're guaranteed to have a more accurate top results. You're sort of continuing to climb up this chain of accuracy. These are methodology ways to improve your search problem, but there's other ways and other considerations. Maybe your data set is a better fit for keyword search than it is for vector search. Like you would have to go about defining what better means, again, through pet queries, question-answer pairs, or judgment lists. It might not always be, like, I think of an example that's a really good one. It's McMaster car. McMaster car is very, very much keyword-oriented. Part numbers that might not have appeared in the training data set of an embedding model. We'll talk a little bit more about that later. But your data set matters quite a lot in terms of what this actually looks like, whether you're actually climbing the computational load accuracy axis correctly. But sort of, maybe some of this was obvious. The reason I'm going through the laborious effort of defining this axis is you really need to be thinking about accuracy from day one when building a search system. And RAG is one type of search system. Before you layer on something new, like lexical search on top of vector search, you need to have a way of defining not just your query latency, but also what an accurate set of results might look like, which again can vary based on your data set. So I think we've got a good understanding of what the database and the search system might be responsible for. Probably important to talk about chat completion models and embedding models. We wouldn't really be having this new interface if it weren't for the capabilities of LLMs like GPT-4 or Anthropic's Claude. I think it's good to take a brief look at what's going on under the hood of these models, both the chat models and the embedding models, to understand what's back in their capabilities and maybe where they might fall short. So when we talk about information synthesis and information retrieval, we have an understanding of what kinds of responsibilities we can delegate to each of these. So trigger warning, we're going to talk a little bit about transformers. There's not going to be a lot of math. It's going to be pretty high level, but I don't want to scare people off. You're welcome to walk out at this stage. But essentially, transformer models are next token, or not all transformer models, autoregressive next token prediction models like GPT-4 or Claude 3 are essentially predicting future values based on past values and also sets of inputs that they've seen previously. So it's not just the next token based on the previous output that I predicted, but it's the next token based on that and all of the weights that I've learned based on my ability to predict entire sentences in the past. We're going to talk a little bit through Jay Almar's lovely illustrated transformer blog post. To give you a high-level overview of encoder-decoder architectures, there's also decoder-only transformer models that are very popular. But essentially, you start on the left side with your inputs. So this input could be is going to be going from plain text of variable size all the way to the other side, which will be the encoder output, which is fed to your decoder model. The input, each word in the input sentence is tokenized and embedded as a row in the matrix X. A series of matrix operations are performed against learned weight matrices to produce query key and value matrices. And these are all added together to produce what is known as the self-attention head. So you generally have many different weight matrices, so many different self-attention units that might have multiple stacks within each unit. That's kind of how you scale up the number of parameters in your transformer model. But fundamentally, you're producing an output, which is these self-attention heads, which get concatenated and multiplied against one more linear layer to produce your encoder output. This encoder output, along with the output of the key and value matrices, is fed to the decoder input and used along with the sample input sequence and the sample output sequence to produce a reasonable output. You have an understanding based on whether or not you accurately predicted at a certain position the next token, and then you backpropagate the loss that's determined from that output during training through the network. You repeat this process, again, considering the previous encoder outputs or decoder outputs as well, and this is fundamentally how you would train a transformer model. What I want to focus on, rather than the mechanics, is the idea of these weight matrices sort of containing all the capabilities of these transformer models. These weight matrices are what we can call parametric knowledge, and this is what kind of defines the ability to reason over many different types of tasks, many different types of inputs, sort of that feeling of a magical experience you have when you interact with an LLM. A good way of assessing parametric knowledge is chatting with an LLM, just seeing what it can do, seeing if it can solve different kinds of puzzles, seeing if it can produce synthetic data based on your inputs. This is a very popular way. Prompt engineering is a way of understanding what you can do with these models without necessarily using the context. We'll talk a little bit more about contextual knowledge, but many different models are out there, and it's definitely been capturing people's imaginations, just seeing what you can do with them, most often meaning what can the parametric knowledge stored within their weights, what kinds of experiences can that lead to? But we still have this important bit, right? RAG is a very popular framework because I don't always want to tune the parametric knowledge to get my data involved in this application. I want to feed it within the context, within the prompts. I want to give it relevant information from my knowledge base, from my MongoDB collection, for some other data source that I'm ingesting into MongoDB. There's lots of interesting papers assessing different models and how they lean more or less on their parametric knowledge or contextual knowledge. There's interesting work from DeepMind about retrieval transformers that try to integrate this process directly. But I think it's helpful to use an analogy, right? Parametric knowledge, contextual knowledge, awesome. But what does this actually mean, and how can I think about what a good RAG output might look like? And I think a log cabin is a pretty good example. So a log cabin, not the most complex thing in the world. You got a bunch of logs, you need to know how to stack them, you need to know how to put pieces of wood in as the roof, create a bunch of angles, put a door on it, sort of a reasonable synthesis problem. And you might think of the knowledge that's required to put the components together as parametric knowledge. And the logs themselves you could consider as constituting the basis of the entire cabin could be considered contextual knowledge. Without these, the right logs, the whole structure kind of falls apart. But knowing how to put it together and having it be a reasonably well-scoped problem, that's also very important. Worth calling out, we're not building this massive, million-dollar mansion with these logs. We're not asking the LLM to go way outside the bounds of what we're aware its parametric knowledge is capable of. We're kind of giving it this scoped down, reasonable task of putting together logs in a rather simple way. I think this is one of the key bits of kind of getting out of customer demos into the world of solving real problems is understanding that at an executive brief level, maybe we talk about AI revolutionizing everything, but practically, when you scope down responsibilities to very specific tasks, it's much easier to build a repeatable system. And it's much easier to get something that doesn't go way off course or produces unexpected results. So we're not building mansions, regrettably. We're kind of treating the LLM a little bit like a toddler, you know. We are taking our huge expectations and we're putting them over there and we're saying, you are a toddler and you are going to build this log cabin given the materials that I give you. I'm not saying you should put like exclamation points in your prompts to like yell at your toddler. I'm not giving parenting advice, but I am saying scoping down the expectations somewhat and being patient and with what you're asking it to do is probably a more likely outcome for getting into production. Essentially, you're taking that information synthesis problem the LLMs are doing with your data, and you're making it very easy so that you can focus on this other problem, which is that we don't actually have these logs. We're not given logs. You got to get these logs. You got to focus on finding the right data to serve to the LLM. And if you can focus on that, you could do a lot more to control the whole problem. If you focus on the search problem and you scope down the LLM to what is repeatable, there's a lot more flexibility you can have in using cheaper models, in trying, different techniques towards information retrieval that might lead to better outcomes. This kind of naturally leads us to information retrieval and embedding models. So we've talked about keyword search a little bit, but embedding models have really captured the imagination of a lot of developers in the past year. These are very similar to sort of GPT-style transformer models. The main difference is that instead of masking sort of the final token that you're predicting, they use something called masked language modeling, where they mask tokens that are sort of randomly selected during training, and the objective is to predict those tokens given the surrounding context. But a lot of the fundamental architecture is very similar between BERT and a GPT. But in this way, you can kind of gain bidirectional context on the masked tokens and represent entire sentences with embeddings, and other types of unstructured data. There's visual bidirectional encoders and audio-based bidirectional encoders that allow you to map other types of unstructured data into high-dimensional vector space, which makes it a lot easier to do comparisons against index documents and query documents. I like to think of the book example, where you have an idea in your head of genres of books, and different types of books likely by description map closely to each of those genres. Great, I've got these embedding models. How do I actually know what to use? You can go with some of these standardized benchmarks that Hugging Face provides. So this is sort of all your open source and closed source models. You can see on various tasks how well they perform. Kind of a tricky problem sometimes because a lot of the open source models in particular are trained on the data sets that they're evaluated on here. So another approach is to assess on your own data set how effective are these embedding models at capturing the relationship between my queries and my answers. I really like this book. It's a very popular software design book, and a lot of my examples will be using sort of query document understanding with chunks from this book. So a reasonable question to ask of a software engineering book is, what are some of the biggest challenges with building software? Now, you might embed this into a query vector and then have a bunch of chunks from the book embedded with their own index vectors. And you can assess, using OpenAI's text embedding 3 large at a certain dimensionality, what the similarity of these vectors would be. And maybe from a first glance, this looks good, but then you're saying, wait, I don't really think this actually answers my question. It's related in some ways, but in other ways, it's kind of orthogonal. It's like helpful information, but not really what I'm looking for. But my similarity score was pretty high. I thought that that was actually a good answer. Similarity scores are actually quite easy to reason about relative to an entire 1536 dimension vector. I can't look at a vector and know what that means, but I can look at a comparison between them, knowing my own data set, and get some semblance of that makes sense or that doesn't seem quite right. Of course, these things are challenging because different embedding models have different proclivities towards rating certain things very high. You might have like a bunch of results above 0.8, so it's hard to set like, static thresholds, but this is meant to be illustrative. This is another, response that was rated pretty lowly, even though it's clearly relevant. So one option is to increase the dimensionality. So this embedding model in particular supports varying the dimensionality to capture more signals in your data. And that might resolve the issue, but you still might have other issues, right? You might try different embedding models. You might find lower dimension ones work, higher dimension ones work a little bit better. Maybe your problem isn't exactly that it's an embedding model, it's that your data set, which is much smaller than what those models were trained on, contains special tokens. I mentioned this before with the McMaster car example. There's many types of data sets that have jargon and proper nouns. This happens a lot in e-commerce where you have the names of brands having terms that mean things totally irrelevant to what that company does. Embedding models tend to struggle with that. They see that term in the context of how humans think about it, not in the context of being a proper noun. So you might say, okay, what do I do in this situation? There's other kind of opportunities here we'll talk about when we talk about hybrid search. Graph relationships and general hierarchies between data is presently quite a challenge. There's research around graph embeddings, and maybe that will be the answer, representing hierarchies within documents. And then similarly, structured data generally is quite hard to map to an unstructured query, right? You take a structured document like a document in MongoDB, and you're supposed to embed it in the same domain as an unstructured query. Generally, these things are quite challenging. I will say the capabilities of these embedding models are always going to be improving, and the hope is that you won't be as limited by what they can do now in the future. But since we live in the world of today, where we're trying to get these RAG apps out of the demo stage and into production, and we cannot be waiting for these embedding models to improve, we have to sort of future-proof our systems in some way. I would say that a lot of these frameworks that are popular for orchestrating embedding models, retrieval, and LLM calls, they are a good place to think about how I might data model, right? How am I actually going to take my unstructured data, chunk it in the right way, and add any additional metadata? I showed Python here because sometimes you need to kind of go off the rails of what these frameworks can do and go even further with what you know about your data set. Data modeling is more than just chunking and prompting. You have an idea of what an index is and an idea of what a good query could be, but you cannot get to that query without ingesting the right types of data. Again, a lot of this is quite obvious, but I think it bears repeating because you see a lot of cases where people take a default out of LangChain, maybe a whole page of a PDF, and they embed the whole thing, and then they throw it in with no additional metadata, and that search problem is just very hard to iterate on, because you're going to just be waiting for an embedding model to be able to eventually represent it exactly the way that you want it to. It's much easier to think about other types of metadata and other ways of representing it to improve the relevance, and not just be solely handicapped by that single embedding model sort of linchpin. Filtering. Filtering is important not just for MongoDB database queries, it's very important for vector search queries. Filtering fundamentally reduces the space of vectors that you would have to compare, which is a great way at improving performance and a great way at improving accuracy. So you might have documents modeled like this, where you have the book title, page number, and the publication year, and maybe you want to filter on the publication year and only consider books relevant to some modern software engineering technique that you have in your mind. A simplified version of the graph traversal that is done with HNSW is exact search. So we will be supporting exact vector search very soon in the product, but let's take a look at what happens when you do exact search with and without filtering, or without and with filtering. You would typically enter the graph at some predefined point, and you would have a query vector that you would be assessing against. You would then do similarity comparisons with each neighbor exhaustively until you got the node that you would yield back. Now, typically, this is a lot of work. When we think of exact vector search, it seems like it's a very expensive problem to be solving. So it'd be nice if we could, before we perform this search, apply a metadata filter and X out any candidate that is irrelevant, particularly in cases where you have a multi-tenanted index structure. Maybe you're building a search system for a bunch of customers. This is a very important step. Here I only have 2 nodes that I would compare, and I would yield back 1. That's half the work. In practice, whether or not a filtered exact search or a approximate greedy search of the HNSW layer occurs depends a little bit on the cardinality of your filter, but most often we've seen that it improves latency, and every single time we've run tests on this, we've seen it improve accuracy. So given that an approximate algorithm, that's the key knob you trade off. Filtering is another way to generally improve and make your search problem easier. So again, we're thinking about what kind of search am I doing, and where does it fall on this computational load versus accuracy spectrum. Axis. Spectrum is one-dimensional, axis is two-dimensional. Hybrid search is another example of improving your search problem with metadata. So there's been some, I would say, anecdotal evidence of this more in the search community around keyword search still being relevant for large amounts of text data, where maybe you have a full page from that software book and embeddings over a smaller scope of that data, particularly because there's only a few embedding models that can capture like thousands of tokens. Most of the lower dimensionality ones are on a few hundreds of tokens. So there's like a number of considerations why you might represent relevance at different levels, and then jointly consider these when you want to get back, say, the most relevant page across a library of content. So this is fundamentally doable in the system today. You could define a vector search index on the documents that contain paragraph embeddings. Define a vector search index on the same collection, and this would yield back a set of documents that contain paragraph embeddings, sorted by the similarity score. You could also do a dollar search, define a dollar search or vector full text search index, and execute a dollar search query to yield back the documents also within that collection that contain that indexed full page content field. You can then jointly consider these and combine the result sets using a method called reciprocal rank fusion. We have a tutorial that has code in our docs about how to do this. I thought I'd save you guys the trouble today. And you can group on a common key. So essentially, your goal is a set of ordered results. And in this case, you're considering joint methodologies for getting that. So hybrid search, again, you're continuing to move along this path. In today's world, these would be executed sequentially via a union with. But we're looking at ways of integrating this into a single pipeline that is easier to parallelize, particularly for limited result sets. Another, again, somewhat obvious but not often discussed way of building additional proxies for relevance is feedback. Right? We deal with search systems all the time. When you go to Amazon and you're searching something, how often you're scrolling through things and clicking on things is considered in your search results. But when we talk about RAG systems, we often think of RLHF, where we're tuning the model weights and letting the model provider figure out how to take that feedback. You can also do that yourself. You can incorporate within your chatbot system citations to the documents that are referenced and allow people to vote on those. This is a good document, this helped me. This is not a good document, why did you show this to me? And consider those within your joint score in a similar way that you could consider keyword search. I sort of think like we're in the early days of like feedback-based RAG systems. Like it's very much content-based today. So I'm very excited for how data modeling incorporates that and kind of improves, again, the relevance of the results you're giving to the model. We're coming to the end of this talk. I do want to reiterate that we really wouldn't be having this conversation today if it weren't for the capabilities of these machine learning models that have made leaps and bounds, particularly as these transformer models have gotten larger. What I do want you to walk away from, though, is the idea that you can make your applications even more capable by not just throwing anything at these models and hoping they can figure it out. You can take control of a lot of the RAG problem through intelligent data modeling and kind of iterating from a solid foundation with a data model and based on the document model that scales with you. So this is a take, but I believe that the data model is sort of the key to being able to iteratively improve your RAG system so that they can get into production. Thank you very much. And I will be taking questions. I don't know where Ralph went. Hey.
All right, everybody, raise your hand if you have a question, and I'll come by with the microphone.
Are there any MongoDB university courses that cover hybrid search?
There are MongoDB university courses that cover Atlas Vector Search. We recently released a unit on it, and we touch it upon it hybrid search as well. Emily Pope is sitting in the front row and was very instrumental in making that happen with some feedback from me. So she's a good person to ask if you have more questions about that.
Question right here.
Hi, are you planning to add RF search in the hybrid search implementation for Mongo?
The current plan is to have default combination functions. So you can define sub-pipelines within this new hybrid search experience. And then if you don't define a default sort of combination function, we will do RF for you. But we're planning on allowing custom logic for when you combine, because you might want to consider the score and not just the rank, right?
Any other question? Right here up front.
What are some of the strengths of MongoDB over other competitors for vector search?
Wow, great question. I would say the main strength of MongoDB is the fact that it's all integrated for you. So vector search and full text search are sort of secondary indexes for getting to your data. So at the very beginning, I showed a database defining an index to make your queries faster. Search systems are a secondary type of index where you consider relevance to get to the most relevant results. But you wouldn't want to have another fully separate type of database to do that, because that's just another type of index. We believe that fundamentally within the same data plane, you can support multiple types of indexes performantly. And a lot of our customers seem to really like that about the product.
That was a great question. Who else has questions? I see over. I'm going to go here, and I'll come back to you.
I have two questions. One is for among all the data model create embedding, right? Which one you think yield the best, most relevant result? First one. Second one, can you elaborate the upvote? I didn't get that part. I think that might be interesting. So, yeah.
Cool. So the question was which embedding models are best, and then the second part was to elaborate a little bit more on the feedback. So I would say it is hard to make sweeping statements about embedding models today. There's blog posts from providers like Cohere that talk about differences between embedding model performance for specific examples, but those examples might not be relevant to your data set. Maybe for your use case, it's, you could use many other types of models, like most embedding models could meet the relevance that you are trying to map, and you're most concerned about cost. Or maybe you want to run on a CPU. There's a few embedding models that run directly on CPUs that you can host yourself. There's like kind of a set of considerations, but in terms of capabilities, I mean, we're going to be talking more about this, I think, when we roll out the map program that Dave mentioned before, but it sort of depends on the system that you have, the type of data that you have, and the clouds that you run on. I have my own favorites, but it's really hard to generalize to, this one embedding model is the answer. We're working on kind of getting there, and the same thing is true, by the way, for chunking. Like, chunking is one of those things that really does also depend on your data. These other general techniques are sort of suggested avenues of exploration, but I didn't talk about chunking at great extent because there's so many different ways you can chunk that itself would be a whole 45-minute talk. And to answer the second question, I was basically just getting at the idea of incorporating user feedback from people that are interfacing with the RAG system into the data model. So if you are able to build a UI that rates the responses you're giving, you can consider that within the document itself. So you're basically just making a database write that considers the interaction a user has with your application. And that, since it sits within the same document, can be considered as another proxy for relevance. But it's user-based, it's not just content-based. This is how a lot of like e-commerce systems work. They bootstrap things with content recommendation, and then they get user feedback to drive content. And of course, they also have things like advertising, which are mostly irrelevant for the types of search applications that a lot of folks build.
Okay, we had another question over here. We have a bunch of questions, so I'm going to make my way around the room.
So as you said, like you can create multiple indexes. So will not it degrade the performance while loading the data?
So the question is, you can create multiple indexes, but will not degrade the performance by loading the data. So I think it depends on what type of performance you're expecting from your app. So a lot of these RAG apps in particular, this multi-index query pattern where you then synthesize things, so in our case that happens in a separate process from the search process, right? We have materialized results and then we blend them together. For a limited result set, it is nowhere near as long as it takes to actually traverse a vector search index. For a very large result set where you might need to like stream results together, it could. But for RAG apps, it's, I would say, unlikely that you would run into performance issues. But there's definitely things that we're thinking about in terms of like nativity of other operations you would perform within the search process. So I just think that this merge, multi-index merge, isn't necessarily like the biggest concern for RAG specifically.
I saw a couple of hands back there, and then I'll come back over this way. So I'm coming to the back of the room here. See how fast I can get to you. Here you go. Welcome.
Hi. We have already built a system that uses MongoDB Atlas, and we does use a vector search, and it works well. But now we have another problem you just mentioned. We can use upvote and downvote to get feedback from user, and indeed we put this data into the document, but we don't know how to do next step. How to collect after collect this feedback. How can we optimize our system to the user? Because user we record user question and we record answer LLM feedback, and we put this data into log, and also user can upvote and downvote in this conversation, but we don't know the next step we can use to optimize for the next time user have the same question, but the answer can be better. We don't know how to do that. Do you have any suggestion?
So in the hybrid search tutorial, we talk about like scaling the weights for the different methodologies that you're jointly considering. So like you're scaling, your keyword search or your vector search. And we have like a full example for how to do that. I think considering user feedback is a very similar thing. You need to build your system, and instead of executing, a hybrid search, you're executing a dollar project pipeline, which scales that user vote to a similar domain as either the reciprocal of the rank from the vector search or the score of the vector search. And then you can jointly consider these things. That's kind of the idea, is like you have disparate query patterns that you can synthesize together, provided that the space that the scores are in the same domain. So you might have 300 user votes. You need to find a way to normalize that to, let's say, a cosine similarity score that's between 0 and 1. And that takes just iteration and testing. But it's fundamentally a knob that we make available to you. I will say we could probably put it together a tutorial for exactly how to do that, given a similar data model. So good feedback.
I have a question here, and then I'll come to you, sir, back there.
Hi, my name is Satish. I have a question with respect to the data model, coming in between the vector and the search. The question is, do you see graphs actually coming there? Do you see this data model coexisting with graphs in future?
Yeah, I think it depends on the nature of your data. So if you were to build a graph relationships between data, you would need to do that at ingestion time. And in MongoDB, you can model graphs of data provided that they're hierarchical. We have a stage called $graph lookup, which you can make subsequent to your vector search. So maybe you retrieve at like a leaf node of your hierarchy, and then you want to retrieve all the way up to some parent node. That it depends on the type of application you have. I will say there's probably more we can do to make that in particular a little bit more performance. But I think, yeah, I think there's graphs plus vector are something that is still relatively new in the space. And we're trying to see like what data models actually make sense for that. I know for a lot of financial use cases, like graph databases are very popular. And so we probably want to find a good way to integrate these, but it's still pretty early for sure.
Okay, coming over. Here you go.
Hi. I see you actually in the data model, you add embeddings with the regular documents. So what would be the size, the impact of the embeddings for the document size? For example, if I have 1,000 words or tokens, what would be the size added to the documents? Would that also impact the queries for operation data? Thank you.
So the document size limit is 16 megabytes in MongoDB. So a given vector, let's say 1536 8-2 vector occupies around, I think, 12 kilobytes within the document. So you could fit quite a few vectors within a document. And relative to the size of the tokens that you're embedding, generally that's quite large. But I have not heard much feedback about people's other query patterns within a data model where they have reads and writes and are doing vector search, seeing a large impact there. But I'm sure at the edge, like there might be some considerations. And again, that comes down to data modeling, like best practices. We have considerations around not having overly nested data generally when doing search. And with vectors, we're trying to be very thoughtful about how we want to do that. Right now, you actually can't search against a nested vector. You have to represent these sort of as their own atomic documents. But we're exploring what kinds of data models it makes sense to provide that.
I think we have one or two more questions. You get time for one or two more?
Yeah.
Okay, great.
Hi, I'm Srikant. So we have the scenario for hybrid search, like if the metadata is in a different MongoDB instance and the vector data is in different MongoDB instance, does it have to be in one database, or can it work across two databases for hybrid search?
So with the hybrid search sort of like recommendation we have today, you can search across two different collections and jointly consider the results. But probably a data modeling best pattern would be to have them in the same collection. And the experience we're looking at building in the future is going to be oriented around same collection, joint consideration. Usually we would want to have data that's queried together, lived together. That's just like a MongoDB truism, or not truism, that's a MongoDB principle. And so we presently support multi-collection joint search, but we're kind of trying to focus and guide people towards single collection.
Cool. I think we have time maybe for about one more question. Anybody? Oh, let me come.
Hello. Hi. I have a question regarding the search and the aggregation, right? But you're putting a lot of effort on the search, and we use a lot of aggregation. And how we are improving your aggregation operators to aid the search capabilities, right? For example, facet operator, I see a limitation where the indexes are not being used when you use facet, right? So these are some of the practical difficulties that we face. I want to see how MongoDB is addressing these issues.
Yep. Yeah, so for search and for vector search, there's definitely operations. For $search, faceting being executed natively rather than as a subsequent aggregation stage can have serious performance implications. We're looking at trying to find ways to push more of that work into the same process that is executing the search. And that takes a lot of time. That But that's definitely an in-process type of optimization we're doing. For dollar vector search, it's a pretty spare interface relative to $search. There's a filter you can define, number of candidates that you would explore, number of vectors, and the index name. It's not much more complicated than that. Pretty soon we'll add an exact true or false flag. But there's not as many other things that we see within a lot of these RAG applications that would make sense to optimize in the same way we might look at things that people are using with $search and kind of push down into a single process those operators. So it's definitely like an ongoing effort, but we're aware of a lot of these issues, and I appreciate you bringing it up, particularly with faceting.
Okay, I believe we're at time. I want to say thank you to Henry Weller. Everybody, please, big round of applause.
Thank you.
It's really great to hear all the excitement around vector search. And I thank you all for coming. There's lots of great talks on all of the stages coming up throughout the day, so please do stick around. I believe it's lunchtime, so get some food. And thank you all very much. Have a great day.